Hi. So I'm going to present recent work we have initiated at the very beginning of this year. And the joint work with two students, Sean, which is a student from Nigeria, very skilled student, some sort of rural network. So you have here his email address, and if you want more details, source code and so on, technical details about the network part, please feel free to contact him. And with Leonard Mtumbai from Tanzania, who performs the part dedicated to the very scanning over the new water. So I'm very pleased of this joint work with the two African students, because it's the occasion to open to new opportunities. So Leonard actually, in fact, is now back to Tanzania. So, in fact, most of the time, especially in the academic world, the definition of breaking cryptography is slightly different from what we can expect at the operational level. I mean, most of the time you don't have to make a lot of mathematics or brute force or computing, large computing time, because most of the time a cryptographic algorithm has some sort of armored door on the paper or cardboard. You just have to go through the wall and you can enter the room. And it is the same for cryptography most of the time. And when you look at the operating system level or at the user's level or at the network level, in fact, you find the significant weakness to bypass cryptography. The second very important point is all cryptography most of the time is developed according to some standards, norms, and tools. And this non-standardization is some sort of weakness as well, since most of the developers are using the same API or the same standards. And hence, if you manage to make an attack successful, it will be successful for many cases. So, at last, it is very important. Most of the time, people say, oh, I have to get the key in order to be able to decipher. That's not always true. We have to remind that, in fact, the aim, the very final aim, is to have the plain text. And you can organize some attacks, a few attacks, that directly access the plain text without caring about the algorithm or even the key. That's why, when you try to break cryptography, do not focus too much on the key. There are probably other methods. So, in fact, at secwest I presented some of new results about how to bypass, for example, PacSec-based encrypted networks, and we have the occasion to test it on military networks, and especially in IP encryptors. It's very efficient, except one. I will not say which one, the French product. And in fact, every time we exploit the fact that either the protocol, either the algorithm are weakly implemented or weakly badly used. So in this case, I'm going to develop a little bit more, and as an application, in fact, there is only one possible network to test for this kind of attack. I will speak about the Tor network. So the working operation scenario, you have an undemocratic country which want to monitor, for example, the political opponents or any small group size, medium-sized group of bad guys. What it is very important to keep in mind that it is a malware-based attack. We do not, for the Tor part, we do not make traffic correlation or tricks already used and studied by a previous author. We use this kind of attack would use a botnet and a malware. So we modify the environment in such a way that an attack is possible. It's very important. So here is the agenda of my talk. So, in fact, if you want to bypass cryptography, you can, I will focus on how to do it with malware. You have two main solutions. The first one is exploit the fact that most of the time, very frequently, especially in Windows environment, secret key or initiation vectors are generated not at the application, cryptographic application, but at the operating system level. For example, the Microsoft cryptographic IPA. And another solution is to directly modify, patch the algorithm on the fly directly in memory, which is very interesting. You can change from very basic thing as a operation mode, for example, for block ciphers, or directly you can change the design. Of course, it will have some impact. I will explain how to manage with this. But working directly in memory leaves, of course, no evidence on the hard disk, and it is very efficient. Having this. Of course, the main interest is to limit your attack in a special time window, and you have to deploy your attack in such a way that you can replay it day after day, month after month, and so on. And of course, the weakness introduced in memory enables from the outside to break the ciphertext more easily. Just collect, intercept the different encrypted stuff, and you just make statistical analysis in cryptanalysis. So we have tested everything on different crypto systems, AES, TrueCrypt, GPG, and BGP. And in fact, well, it's very efficient. But the next question was, is it possible to pervert or to bypass some higher level cryptography, for example, in a network dedicated to that, to the protection of communication and information? So the first solution, in fact, you have once again an interaction, direct interaction, for example, to generate the message key or the session key, and which is provided by external program. So it can be message counter, frame counter, message key, session key, initiation vectors, and so on. And quite all of them, especially in the Windows environment, are provided by the Windows API. That actually is the case in the source code. And in fact, this message key, these initial vectors are very important to make sure that the key is not the same. In fact, you have base key, that the same change every day or every week. And in fact, the pair base key and message key must be different every time. It's very important, otherwise you can practice a very easy polynomial time decryption. So if you want to manipulate the environment, you just have to hook this IPR. So here is a very interesting case, which is drawn from a real attack, which is actually not a public attack, but in fact it was in an investigation case of the Department of Justice. In fact, you inject malicious DLL in some processes, and in fact you just hook the normal function cryptgen random, which is actually a cryptographic function in Microsoft application programming interface. You have here is specified. And for example, let us decide that we want to modify in memory the way message key and initiation vectors are generated, for example, between noon and 2 p.m. just during the lunchtime. So we just hook the cryptgen random function. So of course you can say, yeah, but on the bot side, the receiver, he will no longer be able to decipher. That's not true, because in most of cryptographic protocols, the message key or the IV is sent with the message. So that's not a problem. So most of the time it will be still possible for bot to decipher. Another interesting thing is, for example, to make the IV or message key generation reset frequently in order to have a chunk of single file enciphered with the same ID or message key. Another interesting aspect, which is actually very interesting, very easy to detect and to break. So here, for example, we have developed this kind of malware in which For example, you just fix the message key in such a way that during the convenient time window you have chosen, you have the same fixed key 1, 2, 1, 2, 1, 2, and so on. So all the different message ciphertext will be produced from that, from the base key, which doesn't show during the day, for example, and the message key. So in this case, it is very easy to break, to detect first and to break. So any kind of block cipher in stream cipher mode or true stream cipher can be broken very easily. In fact, we have what we call parallel ciphertext, and we have developed a cryptanalysis library that you have in here, where you can download all the source code, and there are example challenges in order to verify that it works very well. And it is also possible to break it in polynomial time. So every time you collect a huge amount of ciphertext, you just have to use a detection file to find the group of ciphertext actually enciphered with the same IDs and encryption key, and then you break it in a few minutes. So, of course, it doesn't work with true block ciphers that are in ECB, electronic code mode, or CBC mode, which are very different from stream cipher mode. So in this case, how to do this? We are going to exploit the fact that many cryptographic algorithms have been developed according to the National Institute of Standard and Technology Institute, AES cryptographic APA profile. In fact, during the AES contest, the NIST, US NIST, has imposed some sort of cryptographic API, which has become some sort of standard. And now everyone is generally trying to develop according to this API. So we have some sort of standardization in the cryptographic development. So here we just patch the algorithm on the fly, for example, to switch from ECB CBC mode to stream cipher-like mode, for example, CFB or CTA. So of course, in this particular case, on the recipient side, it will be no longer this variable, since of course we have changed the mode only on Alice's computer. But from the experience, in fact, most of the time, Bob say, "Hey, Alice, can you send me the ciphertext again?" And since we work in a very limited time period, most of the time it will be transparent. So, just to go into detail. In fact, most of the time you have a function which consists to initialize the cipher mode, and you have here a byte, which is 0 for ECB, 1 for CBC in most of the cryptographic libraries. So, in fact, according to this mode, you have here, you choose mode and you configure, you set up your algorithm conveniently. And whenever you call after that the block encrypt procedure, then you will take the value and encipher accordingly. And of course, just changing one byte in memory suffices to switch from one mode to another one. And of course, you apply the previous statement. It is also possible to change many things in memory. So for anyone interested, I can send the source code. For example, we have developed a special malware that is able to scan in memory, for example, for AES SBox, and to change with, of course, with values. So we weaken the algorithm in such a way that whenever we intercept the ciphertext, knowing what are the real values of the xboxes, it is possible to perform a far easier cryptanalysis. So you could say, okay, all your stuff is very complicated, since in fact, since you are able to put a virus, you can just tap the key and make it eavesdrop through the network. Well, in fact, it is not very stealth, since you have to open a socket, you have to send traffic. Well, it is not so innocent looking. Here, we just reduce the number of operations. We just modify one bit in memory. We just make operations that seems to be normal or that are not referenced as suspicious. You collect the ciphertext on the outside, and you just perform a cryptanalysis. So this kind of approach is far more interesting if it is stealth. So now, as an application, how we can do this? So first, I would like to be precise because there are huge stupid buzz around our work, while we didn't issue anything. We didn't have anything against or pro the Tor network. For us, it was just the only available infrastructure to test our approach and to test our proof of concept. So it is not intending against Tor because it is Tor. It was just the only solution we had at the present time. So we have performed a lot of security analysis. Well, afterwards, it seems that we have found very interesting things. We have sent everything to the Tor Foundation after some very difficult debate, but they are, and we are in permanent contact with the president of the Tor Foundation, and we send every data. At the time, we don't have many answers. But I will make the source code of the library we have developed and every stuff on the website in a couple of hours. So what is Tor network very quickly? I think that you all know, but just to remind a very important fact. So it is an onion routing system that intends to provide privacy, anonymity, censorship resistance. And originally it has been created and sponsored by the US Navy. And according to feedbacks that I was not able to verify, it is used by normal people, military. It doesn't mean that military are not normal people, but there are no normal use. Journalists, law enforcement officers, and so on. For example, in France, it's of course forbidden to use non-national crypto, so I don't know which kind of militaries can use it, but anyway, it is mentioned on the website. So in fact, you have different possibilities to make IRC, instant messaging, browsing the web. So we can imagine, for example, for journalists being abroad in very difficult countries, Tor can be very efficient, very interesting, as well for political opponents or dissidents. So once again, it is not intending to, I do not intend to say Tor is not a good thing, just a test case. So if we, some fact, it is probably one of the weaknesses is run by volunteers. So what is interesting, we have in fact noticed it very recently, in fact, there are a number of onion routers, but not are active at the same time. In average, only 2,400. There is some sort of combinatorial management of the onion routers, which is actually very interesting. So, alright. So, just to summarize with a few figures, in fact, Alice wants to communicate with Bob, and the computer with the green cross are Tor nodes displayed everywhere in the world. And in fact, every time you want to communicate, you will choose according to different rules, mainly based on consensus, 3 nodes in the world, and they will set up a cryptographic key management and will perform 3 layers of encryption. And whenever Alice wants to communicate a second time or a third time and so on, of course, another random 3 node route will be chosen. From a cryptographic point of view, in fact, we have 2 main parts. We have the Diffie-Hellman part, initial part. We intend just to make, to share a secret key. So it is just typical, something typical. And then all the encryption, once the base symmetrically has been set up, is in AES counter mode, which is a stream cipher mode. From a cryptanalytic point of view, it's not a good choice. It's very fast to encrypt. You just combine a random sequence to the plain text with a XOR operation. But from a security point of view, it's not advised, since if there is some problem in the key generation, you will have parallel ciphertext. whatever may be the reason. But for example, in the past, there was some very similar problem in embassies where the device generating the message key was in failure. So that's why using direct stream cipher mode or stream cipher may be dangerous if you don't control all the implementation. So just to summarize, in fact, you have 3 layers of encryption. So it is figure taken from the official documentation. So you have here the cryptography with the defilement part, DH, and the setup of the AES cipher to negotiate the key. So everything but fast. So as far what about the non-attacks? In fact, non-attacks are considering most of the time traffic correlation, which are very efficient attacks, only theoretical because as our attack, no one was able, even authorized to test it on the actual network for legal reasons. But I think that, for example, the talk of Mike Perry at Black Hat USA and DEF CON is very interesting because there is a lot of reference and is rather complete. You can also visit the Bauer website. There are also very interesting papers. So, to my knowledge, once again, it's not possible to know what has already been done. There is, I don't know, coordinated, multi-level, large-scale attack against network actor. In fact, we have considered this network as a general critical infrastructure. And since we work like a cyber warfare, cyber attack would or could occur, you have to the very first important step is intelligence step, just to have a as complete as possible view of the target and of the network. So the first step has been to have the most complete possible map of the different onion routers. So what about so-called Tor weaknesses? We don't exploit any weaknesses in Tor because it is a rather well-written code. There is no bugs, no flaws, and so the problem is not here. In fact, we could summarize by saying that first it relies on TCP. And TCP is a nightmare in terms of network security. We exploit and we turn back some protection mechanism used by Tor against, for example, to prevent large DDoS. We just turn back against the network. And worse, there is no overall security policy. Just imagine a large company where every user would be free to choose the operating system to set up himself his computer. It would be a nightmare. It is actually the main problem of Tor network. You have a collection of volunteers that decide how the onion router must be configured and used. And it is more a conceptual problem, but using cryptography is part of the problem. Because every time you encrypt your data, you focus attention. You have only communication security aspect, according to the NATO terminology. In fact, you don't hide the channel. So every time you encrypt, you send noise. And sending noise is never innocent. So I think that the solution would to have PacSec, transmission security. So our attack will just try to exploit everything. So, in fact, the main principle is to compromise some nodes and make sure that with a rather high probability that all the 3 node routes will go through those compromised nodes with a high probability. Of course, we cannot guarantee that it's close to 1, but in cryptography, if you manage to break at least 10%, for example, of the traffic, well, it is a success. The typical case would be, for example, someone using a botnet for the first part, China or any other country. I don't have anything in China. And in fact, if we consider, there is a very interesting result from Bigelow. In fact, we say that if you control M onion routers, whatever may be the kind of control, and if you control M onion router over a total number of N, then you are able to control that percentage of the traffic, M over N to the power. So, our attack consists first in maximizing N by infecting them, or installing rogue onion router, and reducing the value of the N, I mean the active onion routers. So in fact, we do not perform large-scale DDoS because it would be very visible, and I think it would be would not be efficient. We just make some surgical strike against given nodes. And the aim to force through 3-node route is to make convenient local saturation or conditional. And of course, when you replace the attack, you can change the subset of nodes you have decided to compromise. So you have some sort of polymorphic network management. So we have validated this on the test network, which is, well, not so big, but I think rather close to the reality. And we are currently developing, with the support of some French institution, a dedicated botnet, which is a proof of concept in order to try to have a more comprehensive view and then to automate the security analysis. So, the first step was to identify a subset of weak onion routers, to install dynamic trapdoor by means of malware, and in order to modify the cryptographic base. So either modify the mode of the malware. But what is important on the hard disk, the onion router integrity is not modified, so there is no evidence left by the malware. Then we selectively try to deny with a high priority access to the non-compromised onion router. In fact, we want to make sure that with the high priority, the traffic will go through the compromised node. So for that, we have designed 3 variants of non-attacks: condition and partialization, packet spinning, and non-pass, and TCP reset attack. So for that part, if we need many technical details, we are going to publish source code, and Sean will be very glad to give you as many details as we may publish. So, in fact, our network just played 50 onion routers and 1 directory server, which will represent approximately 1% of the actual, the real Tor network. So, you have here the map, we will find on this slide. So, during the intelligence step, we try to, once again, have a as complete as possible map of the onion routers. And we have identified slightly more than 9,000 onion routers, where they are, in fact, public most of the time in cache descriptors. And we have managed to extract hidden onion router. I will explain it a bit later. So we have developed a special library to identify all the hidden Tor relay bridge. So you have here the different results. Slightly less than 4,000 are running in the Windows, and on the total of 5,827 physical routers. And until now, we have identified 1,250 directory servers. The actual number is probably a little bit higher, since they are doing some sort of combinatorial management. In fact, directory server are just subset of the all possible routers. So we have made some. I will show you the Google Earth file. less than 60% are within the European community, while around 13% are in Asia. So here's a figure. So I'm not sure that all those there are very interesting questions, because since only volunteers are running Onion router, I would like to know in Iran, who is behind the volunteer, or in Syria, or even in Russian Federation, or in China. Well, it's a main problem. You don't know whether Onion router, which have been installed, are not managed by government or intelligence agencies and so on. That's a problem. And in some countries where the coverage is far high. So you have here different figures about the repartition in the world, in general, left, and for Windows computers on the right. So hereby continue. So, another part of the security of the Tor network relies on the fact that a number of Onion routers are non-public, are hidden. In fact, it is rather clever. It is just to prevent, for example, ISP filtering, or just to make it difficult to block or to deny some nodes. And at the very beginning of our studies, you say, okay, it will be difficult because some of these nodes are very difficult or quite impossible to extract. But little by little, it was obvious that it was possible to automate what is it is planned, it is in the Tor norm. In fact, if you want to use hidden Tor node, you have to make some sort of request on that website, registerproject.org, and we have simply written a script in order to have automatically different Onion routers. So this library is part of the Tor extend library, which is going to be public and written by Sean. So until now, we have discovered 310 Onion routers. So we have here. So this file is available on our blog. So you have a lot of, we have extracted all the different, for example, in Japan. Here. There are 63 nodes here. So where everything is described in the file, you have the IP address and so on. So it's 63. But you have some other very interesting area. You have Syria, there is a number. Well, everything is split into countries. And you have a very interesting part, which is in fact the 310 Tor bridge. Normally it is routers that should be hidden. So for example, you have one here, and you have in very different countries. So and so. So I will let you explore the maps on our website, but we have a complete view of and complete description of hidden, non-hidden, Onion routers, and so on. So from now on, in fact, since during the planning step, we have, in fact, during the intelligence step, we have a description of all the nodes. In fact, now we are going to choose which nodes to infect. So of course, we tried the simplicity. We were focusing on Windows Onion routers, since in fact, many Windows, in fact, is very prone to vulnerabilities or remote exploitation. Another interesting question, you probably not have to subvert some nodes since they are already malicious. and managed by row countries. So, in fact, then you have to go to the conduct of maneuver. You have, in fact, the node, and then you are going to force the root. So, to infect some nodes, in fact, we have made an extensive vulnerability scanning, mainly on the Tor onion routers under Windows. So, of course, we have limited most of the time to France for legal reasons. But we've made some experiments in other countries, very limited, and our statistics shows that in average, 1/3 of the onion routers are badly configured. And figures are different according to the operating system. It is slightly more than 40% for the onion router under Windows, while it is slightly less than 20% for any Unix server. Once again, it is just an estimation. I do not pretend it is the actual figure, but it seems to be rather realistic according to something we have done. Of course, since we use known scanning tools, we do not take into account zero day and so on. Among those vulnerabilities, what is interesting, 20% are critical severity, while for 80% of them it is medium severity. Sometimes it's very surprising because it's proof that in fact you cannot let user decide without overall security policy. When you stimulate some port 443, sometimes you get very interesting things. Certificates are badly managed, and you have the secret key instead of having the public key. Well, not a good way. So I think that the first very mandatory step would be to enforce some sort of overall security policy. So now the second part of the conduct of maneuver for the attack consists in using some techniques in order to force routes through the compromised nodes. So in fact, those techniques have been developed from existing works from academics, but we have modified it, especially Sean, and we have produced 3 original variants. But they are starting from existing works. We have just adapted our special case, which is once again a malware-based attack. So the first consists simply in trying to congest, to saturate locally some nodes. For that, you just take .NET and you target some nodes. So this approach has been first inspired by Murdoch and Danesis at Cambridge University, and later by Edens and Paul. Of course, there is some operational condition. In order, you must have a large number of available onion routers. So very simple, basic, but efficient attack. So you can use, for example, the fact that the Tor clients are using fast entry node. In fact, they don't want to lose time to just wait that a node is ready or there is some sort of timeout management. So it is possible to take it as a criterion. Actually, we are developing a second approach, which seems to make difference between different parameters like uptime, bandwidth, consumption, and to try for 3 categories: high, medium, and low. And so, in fact, I think there are possibilities to improve. So, of course, since we control the compromised node, we make sure that there will not be involved in any 3 routes, and for that we use internal firewall rules. The second approach has been inspired by Papas and different other authors in 2008. In this case, we just send malicious packets, forged packets, toward nodes we want to deny, and in such a way that we are looping them among them in infinite circuit. During that time, any other request for 3-node route will be, during the compromised node here in black, with a high priority. So in fact, I think there are possibilities to improve. So of course, since we control the compromised node, we make sure that there will not be involved in any 3 routes, and for that we use internal firewall rules. The second approach has been inspired by Papas and different other authors in 2008. In this case, we just So you have the description, the way the library is working. So we just have to generate random data for data according to the previous figure. And it works very efficiently. So you have here capture of or test, for example, for 15 opt circuit. We create a circuit of 15 so of course you can scale this according to your version intent. So the third technique is a classic TCP reset attack, even shown as input some very interesting new tricks. Here, in fact, we have exploits what is probably already used by ISP in order to prevent some attack. In fact, we have just mimicked the behavior of classical internet service provider. We forge a TCP packet, we set some flag, suitable flag with the right value, and in fact, we manage in this way to connect strictly using the node we have compromised in the first step. So you have here the approach. In fact, you have the ISP, of course, which will be the attacker actually in your context. In fact, we make some reset, making sure that finally we have this. In fact, we prevent any circuit three node route through the non-compromised nodes, thus forcing the route through the node we have compromised, using some internals, for example, firewall rules and so on. So, of course, we combine all three techniques, since I don't think that only one will be sufficient. So, what about the malware dealing? So you have the botnet or some sort of botnet in order to make the high level and enforcing the root. What about the malware part at every client's level? In fact, well, we have developed a lot of malware technique, but it's very interesting since you have an odd number of onion routers. Here's 3. In fact, every time you put a layer, since the XOR encryption is involutive, in fact, you just have this. And it is, in our context, if you have several texts, or if you reset regularly the secret key, you will have a chunk of parallel text, and then it is easy to detect and to break. For example, if you go in the medieval library, there is a detect single byte. You will have a link how to reset the key frequently in order to have parallel chunk of cybertext. But once again, it's very easy to detect, a few minutes, and to break, approximately a few tens of minutes. It's a real case, polynomial time attack, both for detection and cryptanalysis. So, if I summarize the Tor attack, in fact, we combine in a random way the three techniques that shown at the developed. You can replace it in a reduced time window, and we can replay it every time we desire. We just at the malware part, just activate, deactivate, and so on. Of course, this attack is possible only because it is possible to infect a rather significant number of onion routers. Once again, it is the main aspect of our attack. We do not modify the integrity. Wow. So once again, it is not correlation traffic attack. It is malware-based attack. So that's why I was a little bit sad about all the buzz made against our attack or against Tor, because it's not with the malware. It is obvious that you can perform very efficient attack, whatever may be the strength of infrastructure. So of course, to be really sure, it would be very nice or very efficient to play it on the real network, but no attack can be validated in this way, neither ours nor the previous ones. But there is a very basic fact that we must not never forget. If you have a complete list of all the routers, it is possible to block it just by using local or less local denial of service technique. So once again, it's just very easy. So you can have very clever consensus node in order to select your root. Well, if you know all the nodes, you can block it by DDoS. So we have, during your exchange with the Tor Foundation and with the information gathered from different origin, in fact, we have discovered that some techniques used by the China Great Firewall, especially regarding uptime parameter, bandwidth, could be considered very interestingly, and we are going to develop new version of the TCP reset attack and spinning attack in order to make our approach more powerful. So the source code will be, of course, available by at the end of January 2012. So, well, what to think about Tor? I think that it is not specific to Tor. If you just authorize a large network, but we do not enforce, you do not enforce any security policy, well, you will have many surprises. There is no secret. You must have a general overall security policy. You cannot put your security, make your security rely on volunteers only. They have to follow the guideline according to computer and network security. And of course, if you use operating system, they are prone to have many flaws. At a higher level, it's more conceptual than really technical, but once again, if you use encryption, you focus attention. That's why more and more we are observing that real people who really communicate in a very secure way do no longer use cryptography. They are using steganography. Because you hide the message, but you also hide the fact that you are exchanging a message, which is precisely not the case in Tor, since it is encrypted. So as an emergency measure, I think that the Tor Foundation should forbid Windows on the router, or at least those who are too weak, but it's supposed that to make some fingerprinting and general auditing. Is it possible? I don't know. But it just solves one part of the problem because you don't manage zero-day issues. If possible, prevent the scripting to extract the hidden Tor relay bridge. So it's just an idea, but I'm not sure that it's possible. And for all the part relying on TCP, well, I don't see any solution. So as a conclusion, in fact, and more generally, beyond Tor, in fact, if you want to have cryptographic security, do not look at the beautiful box saying that I have AES 256. Okay, it's just a marketing argument. You have to analyze the source code when available, maybe reverse engineer the application, and in this last case, you will have many surprising features. Most of the time, the way it is implemented is very weak. The actual entropy does not correspond to what is written in the box. Well, it is very important not to focus on the algorithm itself, but the way that it's implemented, used, and especially its interaction with the operating system. So, yes, of course, the power of standard nodes in the cryptographic development must not be underestimated. They are very important. And probably the previous talks have already stressed on that fact. I think that the future of attacks will be several-step attack. I think that using just a single malware, just a single code, and a single step is now a thing from the past. I think you will have more military-like operational planning, operation solve in order to prepare to split the attack in different steps. At each step, look, the end, each step is innocent looting. But it is a combination of these different innocent looting steps that make the final attack. I think, of course, from a combinatorial point of view, it's very difficult to correlate these different steps and piece of operations. That's probably the problem. And I think that we already had the occasion to analyze some sort of this kind of attacks. Well, I think it is almost impossible to detect in some cases. Of course, from the victim point of view, it is quite impossible to identify and understand. And if you want to design trapdoors, you have to do the same. Sometimes two vulnerabilities, when you combine it, can be a trapdoor. So, as midterm work, in fact, we are thinking to prepare or to propose a new generation of Tor. In particular, Sean is about to follow PAV thesis at Cambridge in order to propose to work on some sort of steganography based on Tor network. Well, I think that it could be interesting. Well, everything is here, so thank you for your attention if you have questions. But once again, for the network part, since Sean is very clever and a network guru, please feel free to contact him directly and he will give you plenty of details.
Okay, any questions? 質問のある方いらっしゃいますか?
Do you think the Tor network is going to be really willing to give up 30% of their nodes for that? I mean, do you think the Tor network is really going to be willing to give up 30% of their nodes for the Windows just for the security? It might be maybe a strategy to do vulnerability scanning before they accept nodes or some other thing.
Yeah, well, of course, 30% is in itself, it's not sufficient to subvert the network. We have, of course, to make sure that we go through the components. But I think yes, I think that before accepting unknown routers, if I well understood your question, would be, for example, to accept formally to be audited and to be scanned for vulnerabilities. Yes.
Any other question?
But there are probably other solutions I am not aware of. But that's true that, once again, just imagine a company where every user will be free to choose a computer, to choose the operating system, to choose the version of the operating system, the application, the security setup. Well, I think if there are CSO or here, and you will never accept.
More questions? I have another question for you. I think that there's been some controversy saying whether this is a viable attack or not. My conclusion's up there on the wall. I think it's a viable attack, and if it's okay with you, I think that the quickest way to prove people that this is something that should be worried about is if I'll post the video. If that's fine, I'll make the video public tomorrow or whenever, if you're in agreement.
Oh yeah, no problem. Once again, it's always like in research. We are publishing the source code. You will analyze it. You will make your own ID. You will test it. But well, I think that it is impossible to make an advice without having all technical details.
I would actually, people have been fairly critical of Eric before this presentation. Please, a big hand, because he certainly delivered the goods.